so far that you've had? Every one of them or none of them? Either one's the right answer. But if they haven't talked about compromise, they're fooling you. 104 has to have compromises. Not everything's perfect. Typically in 104 you usually ignore the weight of the beam, don't you? Buoyancy force of the air. Yeah. So compromise between simplicity of the model and the accuracy of the results of the analysis. The model we're using in this lab is first order plus dead time. It's not exact, it's a model. And it's one of the simpler models, and there's one real good reason we use it. That we'll get to next time we meet. By the way, we're not going to meet next week. I'm not going to be here next week. Don't come next week, okay? And also another announcement, we're not going to take a plant trip today for some of you because two reasons. It's cold outside, and the second is I have something else I want to do. The second reason I gave you is more important than the first reason. So we're going to postpone it till next time we meet for another group. How many of you went on the plant trip last week? How many of you think it had any value? Oh, interesting. Yeah, if you took any pictures, put them on Blackboard File Exchange or Picasa or Facebook or something and tell me where they are, because I'd like to share them with everybody. Thank you. Solving a new problem, it is desirable to build a simplified model so we can get a general feeling for the solution. All right, now then, what else did it say on that thing? It said page 15, transfer functions. Let's go to page 15. How many of you have heard the phrase transfer function before? Raise your hand. Good. That means the Laplace transform of the output divided by the Laplace transform of the input. So y over x of s. And we have a transfer function. G of s is a symbol for a transfer function with a general symbol. And we have a transfer function for an FOPDT system. Let me do this. The transfer function for your system is one that you now know because you have k, t0, and tau. And the transfer system, the transfer function is in what domain? Laplace. Y'all are good. How about I give every team one of these things? Would that be all right? One of these papers? What color are you?
Uncle.
Do I have Uncle here? Is that Uncle?
Of course not.
Y'all have what? Orchid and that teal?
It's pretty cute.
And who's lavender? Lavender. And who's this?
Ivory.
That's ivory. Close. Fuchsia down there. Those are the fuchsia. You all agree?
Yes, sir.
Blue. And pink. Gold and yellow. Well, and red. Now, so it says here the system that you have experimental data for has these three parameters: gain, dead time, and first order time constant. You wrote them on these things, right? Everybody say yes, Dr. Henry.
Yes, Dr.
Thank you. At this point, your system value have been determined by you, and you are not to modify them in any future work, unless, of course, somebody tells you otherwise, like a voice, like the voice came to Nathan. Is it a literal voice or like a textual voice?
It was. Are you want?
Pardon?
It was in your instructions online.
Oh. Now, okay. We can't work with this exponential term. Bummer. The work we're going to be doing has to have polynomials and not an exponential term. Fortunately, somebody named Bode a long time ago figured out how to approximate the exponential term with something called the Bode first order approximation. There it is, right there. That's the Bode approximation. Everybody say, wow, Dr. Henry, I didn't know that.
Wow, Dr. Henry, I didn't know that.
So now you know. Bode approximation doesn't appear in the appendix of that book, so I'm not sure it's there, but nevertheless, there it is. So, you can do some algebra to this, somehow or other. Oh, you can multiply these two terms in the denominator out. These two terms you can multiply out, and you'll get a 1, because that 1 times that 1 gives you 1. There it is. And you get a T0 over 2 times tau s squared if you multiply. It's called FOIL. How many of you remember FOIL? First, outer, inner, last. First, 1 times tau s, there's a tau and s right there. First, inner, T0 over 2s times tau s, that's T0 over 2 tau s squared. Inner, outer, 1 times 1, that's this one. And last, T0 over 2s is this one. So this denominator is algebra, FOIL. You can write FOIL on there. Oh, and expand the numerator into, oh, look at this. I changed this around. So I multiplied k inside the parentheses, but then I put the 1 with the s here first. So that's k times 1 there. You with me? Now, here is a diagram for a proportional feedback controller, which we're going to be studying for several weeks here in the lab. Now, whoever draw this, that should be a continuous thing there, and there shouldn't be a gap right there. This is a proportional feedback controller. Block diagram. And for a proportional feedback controller, that's the controller transfer function. Everybody say, well, that sure looks simple, Dr. Henry. It's just a constant.
That sure looks simple, Dr. Henry. It's just a constant.
You're right. Question?
Not yet.
David, question?
Not yet.
David, question?
Isn't that a constant in the Laplace domain?
Pardon?
Isn't that a constant in the Laplace domain?
Yes. And in the time domain. Constants in the time domain are also constants in the Laplace domain. That's interesting. What is a constant? Oh, this is C of S, this is C of S, this is E of S. I should have put E of S in there. That's the error between the difference between the reference point and the output, or set point or reference point. So in the Laplace domain, you take R, subtract C from it, and that's the error. You put that into the controller. The controller is just a constant. You're right, it's in the Laplace domain. So you multiply that error by the constant, and M is therefore equal to E of S times K sub C. It's that simple. Now then, open loop transfer function is what we get if we don't have a closed loop. So the open loop transfer function goes from R to C, and it's just this times this, which is KC times all that other stuff. That's the open loop transfer function. So it's just KC times G of S. KC times G of S. Question? John? Question? Nicholas?
No, sir.
All right. Turn the page over. Something that we call the characteristic equation is 1 plus the open loop transfer function. That's not very hard at all. Everybody say that's not very hard at all, Dr. Andrew.
That's not very hard at all.
You just add 1 to that thing that we have. The roots of that equation in the S domain give us the point that we call the root locus. Root locus is a Latin term. Let me tell you what it means. It means, who said that? It means the location of the roots. Now, so root locus, everybody say root locus.
Root locus.
What's that mean in English?
Location of the roots.
The location of roots. Okay, so now then. So we have that equation that's the OLTF. We just add 1 to it. So 1 plus the OLTF is just this plus 1. That's not too hard. So this is now the characteristic equation. We set that equal to 0 to find